So till now we have learned about confidence interval estimation whenever we are taking a sample from normal population. So now we are going to learn about Bootstrap confidence interval the same way we did for Bootstrap hypothesis testing problems. So here also in Bootstrap you will see the use of Bootstrap when we have to find out the confidence interval for the population parameter, but we do not have any idea about the population from which it is coming or the distribution from which it is coming, or it might be possible that it comes from any other distribution apart from your normal distribution. So in such cases, how can we conduct the confidence intervals? So let us understand. So what happens is that if you have been, what you have been learning so far is that you had a set of data points which was sampled from suppose normal population, and there you suppose that both are unknown. Sigma is known to you, then your confidence, 95% confidence interval is this, right? Where your this is your sample mean, and next this is your z-score which corresponds to the desired confidence level, and sigma is basically the known population standard deviation and is the sample size. Now if it is unknown, sigma is unknown, then we know that the t-distribution comes into the picture. Now this is the traditional method of finding out the confidence interval, and we have used it earlier. We have seen different examples. We have also written the codes for them in Python. Now what happens is, in certain situations it happens that the distribution from which the data is being taken is unknown, or it may even be not normal. Then in that situation the sample mean still remain the point estimate for me, but we do not know what will be the confidence interval estimate, right? Because we know that the confidence interval estimates are built around your sample means or the point estimates. So in such cases, the traditional confidence interval formula you cannot apply. Rather, we make use of Bootstrap method, which allows us to construct a confidence interval for this population mean or any other population parameter without depending on any distributional assumptions. So, like we have done for hypothesis testing, here also we will not make any assumption about the distribution from which the sample is coming, but still we will be able to find out the 95% confidence interval. Suppose if you want to construct a 95% Bootstrap confidence interval, then what do? We have this sample, original sample, and from here we will draw n Bootstrap samples. So if I say n Bootstrap sample, it means that I am going to take different samples from here, from this given data, and it will be done with replacement. So whatever observations are there, I will note it down, I will put it back, and then again I will select it. So we will get Bootstrap samples. I will perform this n times, and each time when I take a Bootstrap sample, I will calculate the mean. Suppose you are interested in the sample mean, you will construct mean. You will calculate mean. Otherwise, if you are interested in variance, you would be calculating that, and for other median or other things, you will do it likewise. Now, whatever means that you have obtained, so if there are, suppose n is 100, so you will obtain the means for each of them. So x1 bar, suppose say till xn bar, so these are the random variables, I would denote x1 bar to xn bar, suppose these are the sample means. And we are denoting here these by ti. So it means that instead of denoting it by these, what I can say is that I will calculate the mean of each sample. I will take the first sample. So first sample, and then its mean will be denoted by t1. Second sample, its mean will be denoted by t2, and so on. I will go up till the 100th sample, and for that it will be t100. Now we are going to arrange these TIs that you have obtained, the means that you have obtained in increasing order of sequence. Why do we do that? Because we have to find out the quantiles or the percentiles from here. Then only you can order. So you want to order the means that you have obtained. So for this, if you are constructing 95% confidence interval, it means that alpha by 2, that is 0.025, is to the left of it, that is the lower point. So it means that this is the point below which 2.5% of the data points would fall. Similarly, if we are considering this 0.975, so it means that 97.5% of the observations are below it, because 1 minus alpha by 2, right? So it would be 0.975. So in this way, we will find out what are the values which correspond to these points. From these ordered TI, we will denote the lower bound as LB and we can denote the upper bound as UB. Okay, and this will finally give me the 95% confidence interval for the population mean or your statistic of interest. If it is anything else, obviously here we are considering mu, so you will consider 95% confidence interval for mu is this. Otherwise, you can keep on changing this as per the statistic of your interest. Whatever you are considering here, that same thing will appear at the end. Okay, so it is very simple. You have the data set. Now here we are not making any assumption on the distribution or anything else. We are just having a data set. Now from that same data set, we have to resample certain number of times. Obviously, it can be done using any software. You don't have to worry about that. And for each sample, you are going to calculate. Suppose you are interested in means, you will consider mean. And you will order those means because you have to find the quantiles or the percentiles. So you need to order them. And then you will look at what percentage of points lie between alpha by 2 and 1 minus alpha by 2. So these two will give you the lower and the upper bound for your confidence interval. So let us consider here, if you are interested in the confidence interval for the population mean. So you have the sample given to you. You will generate the bootstrap samples here. You will find the mean of each of them. Since you are using quantiles to find the confidence interval, you will arrange these means in increasing order and you will denote it by Ti star, so as we have just now studied. Then you will find the value which corresponds to this and 0.975 quantile. So if suppose n is 10,000, then your lower bound would be T star, the value which corresponds to T star at 251, and the upper bound is 9750. You might now notice that why have I written 251 and not 250 in fact, right? Because 2.5% of the observations are below it. So out of 10,000, 250 observations should be below it. So it should be 250th value. Why we are considering 251? Because actually when you are finding this quantile, it is not exactly 250, but it is 250 point something. So we usually, what we do is that we round up the lower bound of confidence intervals, because by doing it we will avoid the underestimation. So we do not want to underestimate the lower limit of the confidence interval, because it will also account for variability and uncertainty which is inherent in the sampling process. In order to minimize or in order to get rid of the underestimation, we round up for the lower bound. However, here if you see 9750, we are not rounding up the upper bound. We are not considering T star 9751. We are just considering 9750. So here we do not want to overestimate. That is why we just restrict to this 9750. So because if you are doing overestimation, then it means that your confidence interval would become too wide and it might be becoming unnecessary for you, right? So in such cases, what we do, the general convention is that whenever you are using this percentile based confidence interval or quantile based confidence interval method, you round up the lower bound that corresponds to 251 and you round down the 97.5th percentile, that is this, right? So it will balance, ensuring that the confidence interval is neither too wide or not too narrow. So whenever you have to find the 95% confidence interval, you have to find the values at 2.5th percentile or 0.025 quantile and 97.5th percentile in the ordered list. Now you can see that if you have a very large sample size, like here you have 10,000, either you consider T star at 9750 or 9751, so these values won't be much different. The difference between these two would be very small. So it will not affect the practical interpretation of your interval. Okay. So, but in general, the usual convention is to round up the lower bound and round down the upper bound. So, this is how you do for population mean. It is very simple. You just have the data. Now you are again resampling and calculating the same statistic, because here we are interested in the population mean. You are focusing on the sample mean. Right? We know this very well from previous few lectures. We know that whenever we have population mean, so sample mean is a good estimate for that. So we start with that. Now we just simply arrange those sample means and we then order them and find out what are the lower bound and the upper bound for your confidence interval. Likewise, if I change it to maybe variance also, here in this case, here you will be calculating the sample variance. Now the sample variances will be arranged in an ascending order, and from there again this step would be performed, that you will find the lower bound and the upper bound, and that will become your confidence interval. Suppose you have to find out the confidence interval for difference of two population means. So you have two samples, Xis and Yi. These are two samples and they are of different sizes. So you can generate bootstrap samples from each of them. Since we are interested in means, it means that I have to calculate the sample mean for each of these bootstrap samples. So the mean of each bootstrap sample generated from Xis can be denoted by Ti, and the one that is generated from Yi's, you can generate it by Ui's. This and this we have. When we are interested in the difference of the two population means, it means that I have to look at the difference of these corresponding means also. Once you have obtained the differences, you will arrange them, and now you will denote it by these Di stars. Okay. Now once you have arranged them, you can easily find out these quantiles, and which basically represent your lower and the upper bound for the confidence interval. Likewise, if you have the lower bound, so it will be this particular value in the ordered list of the differences of the two means. It will correspond to this 251st value, and here it will correspond to 9750. So this is for 95% confidence interval. Therefore, you will get this. Now, you might come across the ratio of the two population variances, then also same process will be there. With just the difference that means will be replaced by the sample variances, and instead of taking the differences of the two means, you would take the ratio. Because Bootstrap is very flexible, it can work with the differences also, any operation that you want to perform, so it will balance that out. So you will find the variance of each Bootstrap sample. We can denote that by, so you have Xis. From the first sample you will have your variances, so I can denote that by V1. From the second sample I will have, so this is from V1 and this is V2. Likewise we will have V2 and W2, and it will keep on going, suppose for 100 Bootstrap samples. Now next what I will do, I will take the ratio of these variances. These are what? These are the sample variances only. The names are VI's and WI's, in fact they are variances. I can calculate this ratio. Once I have calculated this ratio, I can simply order it and denote it by RI stars. Once you have these ordered ratios, ordered values now, you can easily find out 2.5th percentile and 97.5th percentile in the ordered list. Therefore, you will find that 95% confidence interval for the ratio of the two population variances. Now suppose you want to work with the parametric setup. So till now whatever theory we were studying, it was about the non-parametric situation where we were unaware about the population or the distribution from which the sample is coming. But here it might happen that you might be knowing from which distribution it is coming, but it may not necessarily be the normal distribution. It can be any other distribution. So in this case, what we will do is, we take a random sample from the known distribution, from whatever distribution it is there, we will take it. Now we will estimate this theta. Based on the sample, we will make the estimation, and then we will be generating the bootstrap samples from f theta hat. If you remember in the hypothesis testing also, when we are doing for bootstrapping or the parametric bootstrapping, There also we were considering the distributions. Now we were replacing the original theta with the estimated theta. So we were taking out bootstrap samples from that particular distribution. So here also we will do the same procedure. Now from each of the bootstrap sample that you obtain, you will get the estimate theta. So it will be denoted by theta I stars now. The original one is your theta star. Now once you have this, you will get the first sample. Suppose it is x11, x12 up till x1. Suppose n is 50 or something, whatever it is. Then we will have for the second sample likewise x22 and so on. And this will keep on going till whatever number of samples that we want. Suppose 100. Now each sample that is drawn here, it is coming from, bootstrap sample is coming from f theta hat. So now the sample that you have obtained, from there you will now again estimate. First one will be theta 1 star, theta 2 star, and likewise it will keep on going till theta n star. Now you will order all of these. Once you order these in ascending order, you will denote them by theta I star. You can easily find out the 95% confidence interval for them. Similarly, if you have two different populations and you are interested in their difference of the means, then also you will have two samples coming from different populations. Using the sample data, estimate the parameters that you have. You will denote it by theta 1 hat and theta 2 hat. Now you will generate n bootstrap samples from this f theta hat and f theta 2 hat. Okay, it will not be from the original one, but from this one, estimated ones. You will find, suppose you are interested in means, you will find the mean of each bootstrap sample generated from this, right? Mean of each bootstrap sample that you have obtained from here. Similarly, you will find the mean of each bootstrap which is coming from the second one. You will consider the differences. Once you have obtained the differences, what you can do is, you can order them because we need the quantiles. Once you have the quantiles, what you can do? You can finally find out basically whatever is the lower bound and the upper bound, that becomes the confidence interval for the difference of the two population means. You can see that you are 95% confident that the difference of the population mean lies between these two endpoints. Likewise, you can have the ratio of the two population variances also. So here also again you will have these two and you will estimate the parameters over here. You will generate the bootstrap samples from these two now. You will replace that theta 1 by theta 1 hat and theta 2 by theta 2 hat, the estimated values. And you will find the variance of each bootstrap sample that you generate from here. You will denote it by V1 to suppose V1000. For each sample which is drawn from here, you will calculate the sample variance. Likewise, for each bootstrap sample which is taken from here, you will find out its variance. Finally, you will calculate these ratios. We know the next step, that we have to order them and we will arrange it in ascending order. We will find what is the lower bound and the upper bound, and finally these will become the confidence interval estimate for your problem, for the ratio of the two population variances. So you can see here that we are following the same procedure everywhere. Once you have the sample, you are coming from some population, you replace that theta 1 with the estimate of that. Right? We know how to find the estimate. Once you have obtained that, now the bootstrap samples will not be taken from the original distribution which you had with theta, with not the original parameter value, but now you would, in that distribution, you would replace the parameter by its estimate. And now the rest of the samples, the bootstrap samples will be taken from these estimated ones, f theta 1, this new distributions. Whenever you want, you take that particular sample, you find the corresponding statistic in which you are interested. Here it is variance, sometimes it might be mean. And then obviously if it is ratio, you take the ratio. If it is the difference, you take the difference. You order them up. So for ordering, we are just using a different notation because we want like a star is put here. Alright, so we are not, just to show that we are talking about the ordered values here. And once you have the ordered values, you can simply find out the 0.025 value in 0.97. So this basically completes your confidence interval part. We will look at the corresponding codes in the next lecture. And with this, we also complete your course for 12 weeks, that is on Introduction to Statistics. I hope that you learned something from this course, starting from the data collection, summarization, visualization, then we went to your sampling distribution things, all those concepts, and then we moved with those. So sampling distribution was a tool, and if you remember in the very first class or the first week of this course, we learned that if I am doing the data analysis, so if I have to learn from data, so first of all I need to properly collect it, summarize and visualize it, and then I have to analyze it, right, and interpret the results. So the first 3 lectures were on collection, summarization and visualization. After that, in between, we learned about the sampling distribution, which meant that we are learning a tool in order to do the data analysis. Then we came on to the data analysis part, which included your point estimation, hypothesis testing and confidence interval estimation. So these all come under the concept or the theory behind statistical inference. Okay, so all these are part of estimation and hypothesis testing in the statistical inference branch. And we have seen the corresponding codes also for all of these. Whatever we have studied in this course, we have also looked at the corresponding Python codes. So I am hoping that this course will benefit you in future. Thank you.